Okay, let's get started. How are you guys doing today? Okay, couple things to mention. One, the quiz is on Monday, the big class, and in terms of seating and all. Now, the plan for today is to go over a review. We didn't do this for quiz 1 or quiz 2, but when I taught a similar class like this before, I found that a lot of the students like these reviews. So I'm going to try this quiz and see what. Right? The idea is we're just going to go through the concepts so that everybody can make a checklist and figure out whether you know how to apply these concepts to problems. Right? So we're going to go kind of quickly. You probably won't be able to keep up writing what I have here, but these notes are on the D2Web website right now, okay? And it's in the folder reviews. There's a quiz 1 review, quiz 2 review, and now a quiz 3 review. Okay, so we'll start off with net force. By the way, before I start this, are there any questions? Questions at all? Yeah, it seems like it's always doing that, so I'm rebooting it now. And it will, in 40 seconds, it will be up. It's fine when I come in and then I plug my laptop and it shuts off for some reason. I'm not sure why. Okay, net force, the sum of all forces on an object, okay? So the net force, you have to add up all the forces. You do the components in the various directions to get the net force, okay? Newton's first law, if the net force on an object is 0, then the acceleration is 0 and the velocity is constant, okay? Net force is 0, that means acceleration is 0, that means the velocity is constant for the object. Okay. Newton's second law. Newton's second law is pretty much going to be used in most of the problems on quiz 3. Okay. The way you use Newton's second law, you say F net is equal to ma, that's one of the equations. The other equation will be F net is equal to the sum of the forces. So if you're not if you're not doing those two things, you're not doing the game right, okay? You have F net is equal to ma, and then you have F net equals the sum of the forces, and then you put them together. All right? Okay, so m is obviously the mass, a is the acceleration of the object. Go on. So this is applied to all the components. So you look in the x direction, you look in the y direction, or maybe even the z direction. If you're working with an inclined plane, which we'll talk about in a moment, you might be talking about parallel to the plane or perpendicular to the plane. Okay? So you do each component. F net x is equal to max. F net y is equal to may. Very often the motion is in only one of the directions. Like, if you know something is sliding along the horizontal surface, there's no net force in the y direction. Because there's no acceleration in the y direction. So very often one of these things will be F net x or F net y will be 0. And that's usually where you start from. Okay. Everybody good on that? Any questions? By the way, when I ask it, are there any questions? I'm not just asking people who are confident in this to say yes. I'm asking the people who aren't really following it to voice their opinion if they don't follow it. Right? So if you really don't get it, please really do tell me so that I can try to help you out in class. Because if I don't help you out in class, how else can I help you out other than outside of class? That's not so efficient. Okay. So is everybody following this? All right. Now, so in solving problems, we apply F net is equal to mass times acceleration to individual objects as well as combination of objects. All right. So consider, for example, the case where I have 2 masses on a string. Right? You can also consider the case where I have 2 masses that are being pushed by, well, let's do it here. Two masses that are being pushed on one end, okay? That's another type of situation. And what we can do is we can analyze what's going on either for an individual mass or for both masses together. Okay, so let's consider what would happen if I look at just the individual mass m1. And we know m1 and m2 are accelerating together. So if we have them connected by a string, they accelerate together. If they're pushing each other, then they are again accelerating together. Okay? And so if I look at m1, and there's just going to be the force of this string that's pulling on m1. So I have, let's call it F1, pulling this way. Then m1 is the mass, F1 is the force. Let's say I have an acceleration a. Then I have that the net force on m1, there's only one force I'm drawing here, so it's F1. So F1 is equal to m1 times a. Okay. Now we can also analyze what's going on with both masses together, and very often this is the place where you start. So if you start a problem like this and you don't know the tension in between the two masses, you start off with both of them together as one unit, because then the tension doesn't matter. Okay. So now we look at m1 and m2 together. We have this force F2 on this side pulling it, and let's say the acceleration is a. Then we have F2 is the net force on this sum of the masses together. It's equal to mass times acceleration, but in this case we have m1 plus m2. Okay. Any questions about this? Everybody good with that? Okay, and the acceleration for this case and the case with the single mass is the same. So you can, for example, start here, get the acceleration, then you can go here, and then figure out the tension in the string between the two masses. Or if you're doing a problem where you're pushing the masses together, right? If you're pushing them together, you can take both masses together and figure out what is the acceleration that you get from this force. And then you can figure out, once you know the acceleration, look at this mass and figure out the force that this mass is exerting on it from the acceleration. Any questions about that? We good? All right. Now, if we talk about gravity, then gravity points straight down. So this is the positive y direction. Force of gravity is Fg. That's just m times g. Right? I call it Fg. So g is positive 9.8 meters per second squared, but it points down. So if we were talking about the y component of Fg, it's minus mg. Questions about this? Okay, now talk about tension. So the force that a rope or string exerts as a pull on each end. Okay, if you look at it here, I have, let's say, two masses. We have the tension pulling this way, also the tension pulling this way. Now, Newton's third law says that the force acting on object 1 due to object 2 is equal to the force acting on object 2 due to object 1. So if I have somebody pushing against the wall, this person is pushing the wall with force 100 newtons, and the wall is pushing back on the person with a force of 100 newtons in the opposite direction. Now, similar to this, we have the concept of a normal force. If I have a mass sitting on a table, we have the force of gravity that's pulling the mass down. Okay, so now, but it's being supported by the table. The table is pushing with a normal force Fn. Okay, now, the fact that the table pushes the mass with Fn tells you that the mass is also pushing the table with Fn. Okay, that's Newton's third law. And because because this object is just sitting on the table and not accelerating in any direction, Fn must be equal to Fg in magnitude. Okay. Questions about this? Yeah. The normal force. Okay, so here it is. I didn't actually say it yet. So normal force is the force on a body from a surface that it presses against. It's perpendicular to the surface. Yeah. And normal force is just the force that a surface pushes against an object. So it's not directly related to Newton's third law, but you can put it together with Newton's third law and say the object pushes the table with the same. Okay, the next topic is inclined planes. So if we have an inclined plane with an angle theta here, yeah, question. Uh-huh. Yeah, okay. To be honest with you, the Newton's third law is not all that useful. It's basically Newton's second law that we use all the time. Newton's third law only is when you have two objects touching each other, okay, or pulling on each other from strings. And if this person or this object exerts a force on this exerts a force on that with equal magnitude but opposite direction. That's all. Yeah, but if you want to solve the three boxes on the table, it's not really Newton's third law that you do much with. It's Newton's second law that you use most of the time. Okay, so if I have boxes on a table, we don't need to do three, but we can do two here. Okay, what we do is we say, it's all Newton's second law that plays the role here. Okay, so if I have M1 and M2, what you say is, okay, let's consider both boxes together. Okay. Both boxes together, it has a mass m1 plus m2. So gravity will pull down with a force m1 plus m2 times g. Okay? Now, this table has to push on the bottom box to counteract that force. Okay? So as a result, on this surface here, the table must push with a force Fn that's equal to m1 plus m2 times g. That's not Newton's third law. That's Newton's second law. Yeah. Okay. And now, if you want to know how much force does the M2 block have to exert on M1, that's again Newton's second law, because there's a force of gravity pulling M1 down with M1g. So there must be a force, normal force of M1g pushing up on it. Does that make sense, everybody? Newton's third law gets a lot of play, but in terms of actual use, it doesn't do a whole heck of a lot. Okay? It's Newton's second law that pretty much is used throughout. Other questions? Okay, so now let's look at inclined planes. If I have an inclined plane like this, then the angle is, we call theta. Then we have the normal force that's perpendicular to the surface, okay? And that angle is theta as well. It's the same angle. And we have gravity going straight down. The normal force is going perpendicular to the plane. So that's what I say here. Fg points straight down vertically, while Fn makes an angle theta with vertical. And the strategy is that the motion is completely along the surface of the inclined plane. It's along the surface. So we decompose all forces in terms of components parallel and perpendicular to the plane surface. Okay, parallel and perpendicular. So that's what I've shown here. So you can think about having parallel components parallel to the surface and having perpendicular components perpendicular to the surface. This is my symbol for parallel, this is my symbol for perpendicular. And so we can take gravity here. We have a component that's going to be going down the plane parallel. So that will be Fg sine of theta down the plane parallel. I guess I skipped down to here. Down the plane parallel, negative Fg sine of theta. I'm taking this to be positive, and this to be positive perpendicular. And then Fg perpendicular to the plane, that we have this component here that's going into the plane, so I have negative Fg cosine of theta. It's cosine because it's the adjacent side to this angle here, theta. Okay. Any questions about this? Is everybody good on these components and everything? Okay. Any confusion? Any questions? All right. Okay, so now the normal force is simpler. It just goes perpendicular to the surface. So the perpendicular component is Fn with positive sign. The parallel component is 0. It doesn't have any parallel component. Okay. All right, questions about that? Next, we talk about friction. By the way, the topics I'm trying to summarize here is, in my opinion, the important things you have to, the basic things you need to know, and will be tested on the quiz. In the homework, there's a lot of, your homework assignment is rather extensive. There's a lot of sort of discovery as you do the problems. I'm not emphasizing the little things in those homework problems because I'm not considering those as truly essential to the course material. Okay? So the things I'm kind of focus on here are, if you don't know the things I'm covering, you probably have to go back and look at it. Whereas if you don't know how to do, let's say, a difficulty 4 problem in homework, don't sweat too much over that. Do you understand what I'm saying? Okay? Okay, friction. Static friction is the first thing we talk about. So static means not moving. So that's a force preventing any sliding motion. We call this Fs, sub S for static. And it's now the maximum possible value for the magnitude of the static friction force is Fs maximum. Okay, and if the object is pushed with force parallel to the surface that's more than this amount, it will slide. So if I have some, there's some maximum static friction force here. If I push more with it, it will start to slide. Okay. If I press with not enough force, then it will not move. Okay, so we can say something else about the maximum static friction force. Fs maximum is proportional to the normal force Fn, and so that constant of proportionality is what's called the coefficient of static friction, mu s. So Fs maximum is equal to mu s times the normal force. All right? So very often, if there's a problem with friction, you have to do something with the normal force to figure out what the friction force is. So when you do some force with friction, very often you should start off by trying to figure out what the normal force is. Otherwise, you have to go back and get it anyways. Okay. So mu s, if I write it in a different way, is the static friction force maximum divided by the normal force. Okay. Questions about this? Very confused. Okay. All right, now the kinetic friction is the sliding motion. So kinetic means sliding motion, and that's the friction force that occurs when it's sliding. It's when the object is sliding. So it's a force that tries to stop the sliding motion. So if the object is sliding this way, then the force of kinetic friction is going in the other direction. Okay, so it's opposing the sliding motion. So Fk, force of static friction, kinetic friction, is mu k times Fn. It's again proportional to the normal force. And so this is the coefficient of kinetic friction, mu k. So mu k is the kinetic friction force divided by the normal force, Fn. Okay. Any questions about this? Very good. Okay, next topic. We're going to talk about accelerating frames. All right, suppose we're in an elevator and the elevator is accelerating upwards. Okay? So then I am, let's say, well, some person has mass m. All right? And now what we're going to do is put this person on a scale and ask, for example, what is the normal force that the scale exerts on the person? Right? So now what we do is we analyze the forces, the vertical forces, since there's no real horizontal forces. The vertical force is acting on this person. We have the normal force pointing up. We have the force of gravity pointing down. Okay. Now, we apply Newton's second law. So remember how Newton's second law goes. Remember I say in one case you write F net is equal to ma. So I have F net y is equal to may. And then I have F net y is equal to the sum of the forces. So that will be Fn, which goes up. We have Fg that goes down, so we have Fn minus Fg. And then we say this is equal to that, so we have Ma is equal to Fn minus Fg. Okay. And then we have Ma is equal to Fn minus Mg, because Fg is just m times g. And so we can solve and get that Fn is equal to Mg plus Ma. Right? Now, in your textbook, they like to say, then as a result, it looks like G is changed from G to G plus A, but you don't have to do that. Okay, so Any questions about this? So the scale ends up pressing with a force that's greater than mg. It will be mg plus ma. Now, if the elevator is accelerating downwards, then you do the same thing. You have normal force going up, force of gravity going down, but the difference is that the F net y is equal to minus ma. So I've defined a as being positive here, and so I'm putting the minus sign in to reflect the fact that it's going in the negative direction. Okay. All right. Now, so now I have the net force is again Fn minus Fg. So now I have minus ma is equal to Fn minus Fg. I'm taking this guy here and this guy here. They're equal to each other. And so now I can solve for Fn. Fn is equal to mg because Fg is equal to mg. And I have mg minus ma. So the scale will press with a force that's less than the weight of the person, less than mg. All right. Any questions so far? Everybody good? Okay, so let's go on. Now let's consider pulling an object at an angle. Okay, so let's say I have the string here pulled with tension T at an angle theta. Okay, and so let's say the mass capital M is being pulled by a string with tension T at an angle theta from horizontal. What is the normal force exerted by the frictionless horizontal surface? Okay, what is the normal force? Okay, so I can take a look at the forces acting here. I have T, I have the normal force, I have the force of gravity going straight down, and I can get the x components and the y components. I have x and y directions. Okay. So now what I will do is I will take a look at the y direction, okay, because there's no motion in the y direction, it's simpler. And so I say ay is equal to 0, no acceleration in the vertical direction. So I have F net y is equal to may, which is equal to 0. So now what I will do is I'll look at all the forces in the y direction. So I have Fn, so I'll have net force in the y direction is Fn with a positive sign. I have minus mg because it goes in the negative direction from the weight. And then I have this component of the tension, that's this vertical component, because it's opposite to the angle theta, so I have t sine of theta. So I have now two equations for F net, sorry. And so I have Fn plus t sine of theta minus mg is equal to 0. I can write down an equation then for Fn in terms of mg minus t sine of theta. Okay? Yeah, question? So, yeah, the normal force is only pointing in the y direction. Yeah, there's nothing parallel to the surface. Yeah. Okay, so let's suppose you're asked a question. If I was to compare Fn with mg, is it greater than or less than or equal to mg? Does everybody see that? It's less than, right? Because you start off with mg, you subtract something that's positive, it's got to be less than. So, suppose I ask the question, what is Fn compared to mg minus t? Would it be less than, greater than, or equal to? Yeah, so what do you think? Would Fn, if I compare Fn versus mg minus t, would it be bigger than this, less than this, or equal to this? Okay, so let's say the angle is is not 0, it's not 90 degrees, so if you're a little confused, okay? Okay, so the way you analyze it, the sine of theta is between 0 and 1. Okay, so it's less than 1. So you're subtracting something that's not as big as t. If you subtract by a smaller number, the answer increases. Okay, so it'll be actually bigger than mg minus t. Right? Questions? Okay, let's go on. So if we have a problem with strings attached to a vertex, something like this, we've done this problem as well. So we have 30-degree angles here with the horizontal. So find the tensions T1, T2 if the 10 kilogram mass is hung as shown. So we focus first. So first of all, let's try to figure out T2. And that's simple to do because that's just a string that's attached to the 10 kilogram mass. Okay, so we have the 10 kilogram mass. We have the force of gravity going down, which has a magnitude of 10 kilograms times 9.8. And we have this tension pointing up with the force T2. It's not moving anywhere. It's not accelerating. So therefore, F net y must be equal to 0. And so now we have F net y also equal to T2 going up. And then we have negative 10 times 9.8. That's just the weight. And that must be equal to 0. Okay. And so now we can solve for T2. It's just the weight of the object, which is 98. Right? Everybody's good on that? You could have done that much quicker than I did. You just say it's equal to the weight of the object, so it'll be 10 times 9.8. But now you know T2, so now you can get T1 by analyzing the x and y components. Okay, the x components are kind of simple because they just cancel out because of the symmetry of the problem. But however, for the y components, I get here T1 sine of 30. I get a T1 sine of 30. Okay, and so the net force in the y direction must be equal to 0 from this point here. So I have T1 sine of 30 from this guy. I have a T1 sine of 30 from this guy here. And then I have a minus T2 going down from the T2 guy. Okay? So this must be equal to 0 because it's not moving. And so I have 2T1 sine of 30 is equal to T2. So it turns out that T1 is also equal to 98 newtons. Any questions about this? Pretty good. All right, now suppose you have a problem with a pulley. Okay, so let's say we have one pulley here, frictionless pulley, massless string, and then we have one mass that's hanging, and we have one mass that's on the frictionless surface. M1 is the mass here, M2 is the mass there. The suggestion I made was to consider this positive direction. I call it the S direction if you want. Okay, so now on this side, we have the M2, the force we have. Okay, so the first thing I suggest you do is you look at both masses together. You look at both masses together as a unit. And now what we do is we consider what are the forces acting in the S direction. So we have only this weight of this object is pulling in the negative S direction. Okay. If this is positive, then it's going in the negative S direction. So then I have the net force in the S direction is minus m2g. And then we apply Newton's second law. We have both masses together. We have m1 plus m2 times the acceleration of both masses together. And so now we have two equations for F net S. We have m1 plus m2 times as is equal to negative m2 times g. And so now I can solve for as, and I get negative m2g over m1 plus m2. Okay. Any questions about this? Yeah. Yeah. Yeah, we're going to do that in just a second. Yeah, we're going to do that. Okay. Yeah. Any questions about the acceleration so far? So it turns out this is the acceleration, and it's going down because on this side here, it's up was positive, so it's going down. To find the tension now, what we do is we know the acceleration. We can now focus on what's going on with this mass here because there's only going to be this force of the tension, and we can analyze what that tension is quickly. Okay, so these vertical forces don't do anything in the positive S direction. We can ignore them. So we just have the tension going like this in the negative S direction. Positive S is this way, and so T is going negative. So we have F net S is equal to minus T, and that's equal to M1 times the acceleration AS. And so I have T, now so I have this guy is equal to this guy, so I have T is equal to minus M1 times AS. And I have AS coming from up above here. And so I have minus M1 times minus M2G over M1 plus M2. That's just this thing here. This was AS. So I get M1 times M2 times G divided by M1 plus M2. questions about this? Everybody good? Okay. We go on. So you're probably getting the sense we covered a lot of material in quiz 3, right? So uniform circular motion. This was already quiz 2 material, but then we added forces, right, centripetal force. So uniform circular motion. So it's important that you have these concepts down. If you didn't get it from quiz 2, hopefully you can catch it here with quiz 3. Okay? So uniform circular motion means you have constant speed going around. The velocity is changing in direction, but the magnitude of the velocity remains the same. Okay? We have an acceleration that points towards the center of the circle, and the magnitude of the acceleration is v squared over r. So the direction of the acceleration also keeps changing. It keeps pointing to the center of the circle, but the magnitude will remain constant as well, v squared over r. Now, if you think back to your homework, you were also asked things like whether the tangential velocity was changing, and the tangential component of velocity does not change, because the tangential direction is exactly the same direction as the way the velocity is going. So the tangential velocity was the same as the speed, the magnitude, the whole thing, the whole magnitude of the velocity. Okay? Other things you're supposed to know is that the circumference of a circle is 2 pi r. If you don't know that, it's not on the equation sheet, so remember that, 2 pi r. Okay? So if you want to know how long it takes for the particle to go around the circle, you need to be able to do a calculation like this. The period, the time to go around, it's just the distance divided by the speed. Okay? Right? Distance divided by the circumference divided by the speed. And if you want to know the frequency, that's how many circles or cycles per second, or circles per second. Then you just do 1 divided by the period, and you get the number of circles per second. Okay. Any questions about this? All right. Now, we have a centripetal force. So in order for the particle to go around the circle with uniform circular motion, we need an acceleration a. Okay? And that we said with this a here. So the net force by Newton's second law is m times a. If we're looking at the magnitude, the net force is m times a, which is m times v squared over r. This is what we call the centripetal force. It's just the force required to keep the object going in a circle with uniform speed. And it points towards the center of the circle, just like acceleration. Okay. Any questions about this? All right, is this helpful? Is it helping you? Okay. Even though you know this, sometimes just hearing it again helps. At least it makes you feel better. Okay, so let's go on. So if we have a ball on a string, goes, let's say it makes a horizontal circle. Then we have, there's a speed v here, it's uniform. We have the acceleration pointing inwards, we have the net force pointing inwards. And so the centripetal force is provided by the tension in the string. Okay? So remember, centripetal force is just the required net force to go around in a circle. Now, if we had a vertical circle, so suppose this was in the positive y direction, vertical, then it's a little bit more complicated. So if we have, let's say, a string ball going around with some speed v here, mass m, in that case, we have both gravity. We have gravity, which is mg, and we also have the tension from the string. They both together contribute. Okay? They both are forces acting on it. And so in that case, we need the net force, again, to be mv squared over r. However, both of them, the net force is the sum of the two of them together, mg plus t. Okay? For simplicity, I'm taking the negative y direction this time to be positive, so that there's not. If you want to take this to be positive, then there's a minus sign here, and there's a minus sign there, minus sign there. Everything has a minus sign. Okay. So for a vertical circle, it's more complicated because then you have gravity also takes a role in some of this net force. Okay. Questions about this? All right. Now, if we have an unbanked curve, in other words, a horizontal surface, and you go around a circle, then the centripetal force must be provided by the static friction force between the tires and the surface of the road. So the static friction force needs to be mv squared over r. Okay. Questions about this? All right. Let's go on. Next topic, we have drag force. All right. So we just had a formula that goes with this drag force. I think these problems are rather straightforward because we don't really do much with them. Okay, so if we have an object going with speed v, if it's going very fast, then there's a formula that describes the drag force or the air resistance force from some fluid, either liquid or gas. And the formula is that the force, it goes opposite to the direction of motion. It's 1/2 times c, which is the drag coefficient that will be given if it's needed, and times rho, the density of fluid, which will also be given if needed, and then times the cross-sectional area. Okay, we expect you to know pi r squared is the area of a circle, but yeah, hopefully you know that, right? Pi r squared. And the speed is v, so just 1/2 c rho a v squared. So one type of an application is terminal velocity. If somebody's falling, so let's determine the terminal velocity of a. This is a good problem for just applying Newton's second law. Determine the terminal velocity of a 75 kilogram man, with a cross-sectional area of 0.18 meters squared. The drag coefficient is 0.7, and the density of the air is taken to be density area is taken to be 1.21 kilograms per meters cubed. Okay, so terminal velocity means that you've gone so fast that you're not accelerating anymore. The force of air resistance is canceling out the force of gravity. Okay, so you have constant velocity, acceleration in the y direction is 0, and then F net y is equal to 0. So the drag force and the force of gravity cancel out. So let's take this to be positive y direction. So net force in the y direction is the drag force going up. We have the force of gravity going down. So the net force is equal to 0, and so therefore the drag force is equal, drag force minus the gravity force equals 0, and so the drag force is equal to the gravity force, which is mg. So we're going to just say the drag force, which has this complicated formula, is also equal to the weight, mg. Okay. Any questions about that? It's just the drag force balances off gravity. And now we just plug in things. We have 1/2, the drag coefficient is 0.70, the density is 1.21, and the area is 0.18. These are all given, times v squared, times the mass of the man, 75 kilograms, and 9.8 for gravity. And so we get v squared is 99,642, and then the speed is 98. Okay. Questions about this? It's following? Okay, then we talked about impulse. Okay, sorry, I skipped one side of this. Then we talked about linear momentum. Linear momentum is written as small p. The vector is equal to the mass times the velocity vector. In terms of components, px is equal to mvx, py is equal to mvy. Okay? Just mass times the velocity. The impulse is just the change in momentum. So we give it a fancy name, but it's just delta p. All right? Impulse, capital J. And that's the final momentum minus the initial momentum. If the initial momentum is 0, then it's obviously just the final momentum. So let's suppose we know we're looking along the x-axis, and we have this formula that we wrote down that the impulse is equal to the integral of the force with respect to time, from some initial time to some final time. So we might have a curve like this. Okay, so we have fx as a function of time versus time. Sorry, that was redundant. F sub x versus time. And so let's say it has some curve like this. And then if we want to calculate, if we calculate the area under the curve, that gives us the integral of fx with respect to time, right? You can break this into triangles and calculate the area, or use the trapezoid rule for area. And that gives us the change in the momentum. Okay, so that's just p final x minus p initial x. And so remember, p, the momentum, is just mass times the velocity. Okay, so if you want to find the velocity, you can get it from that. Then we had only one other thing with regard to linear momentum. We had conservation of linear momentum. For any isolated system, the total initial momentum equals the total final momentum. For example, if we have two objects colliding, Then we have here M1, V1 initial, M2, V2 initial, and then we have M1 and V1 final, M2 and V2 final. Okay, so here I have a demo that will show that case. So we could do a collision between two objects. We could have something like that, very symmetrical. Okay, we could have a less symmetrical case where this one has more mass, but let's say the same velocity, and notice how to be different. Okay, so you calculate the total initial momentum of the whole system, and that should equal the total final momentum of the whole system. And that's encapsulated in these equations here. The total initial momentum is M1, V1 initial, plus M2, V2 initial. And then the total final momentum is M1, V1 final, plus M2, V2 final. Okay? And the way you use it is in terms of components. You just do the total initial for X components. Then you do the total final momentum X components. And then you do it for the Y, and then you do it for the Y final. Okay. Questions about this? Now you can also have a situation where the objects stick together. And so that's another situation where, let's do it this way. I have an object coming in, and it sticks. And you can calculate what is the velocity of these objects when they're stuck together. You do it the same way. Oops, except that in the final case, the objects move together. So you add the masses together. Okay, so we have, this is what's called perfectly inelastic collision. We have M1, V1 initial plus M2, V2 initial, the same thing as we had before. That's the total initial momentum. But in the final case, they go together. So you add the masses together. So you have M1 plus M2 together times V final. Okay. Now, if you had sort of an explosion problem, it's the other way around, where this is the initial configuration where it's all one object together. And then the final case is you have these things flying apart. Okay. Any questions about this? Questions at all? Okay, so you have 4 days before the quiz. As I said, a very good thing to do is, so now we've gone through the reviews. I don't have to tell you to look at the review. You've already gone through it. If you haven't done the practice quiz, do the practice quiz. It will help you get ready for quiz 3. Then take a look at the solutions. If you need help understand the solutions, I've recorded a video for the detailed solutions where I go over them. So do that at the very least. And then after that, do some more problems. There's about 70 problems I suggested for quiz 3. I sent that in your email message. Try to do as many of those as possible. If you can do these problems regularly and well, you do well in the quiz. If you don't do well on the practice quiz, you still don't know how to do those problems, you're going to pretty much not do well in the quiz. So it's just a matter of getting to that level. So I'll see you guys next time.